Hello everyone, my name is Naren, and in this session, let's learn system design for Dropbox or Google Drive or any of the file sharing and upload services. And here are the features which we want to support for this particular design. So users should be able to upload and download the files which is there in the sync folder, or he should be able to upload a single file and download the single file also. Along with that, he should be able to delete, he should be able to update, and also you should be able to kind of write, rewrite, and all this kind of operations. Along with that, the very important feature is like history of the updates. So what he needs to do is he also wants to look at the history of the updates to the file. Say for example, if he has a file of text file and he had made up a lot of updates to that file, he wants to see what was the last update I made 1 week before or 1 day before, or what is the latest update as such. So these are the main features which I want to support. Along with that, maybe we also want to support API integrations for our services. Say, for example, if I want to have an API, using that API, I can upload and download the services, such kind of services. So my idea for now is I'm not going to talk a lot about web kind of services where in Google Drive, right? You can use web services and upload and download. So it just increases the complexity of the system design. Instead, what I'm going to do is I'm going to think of, there is a client, okay, in which there are a lot of services, and using that client, like a sync client, in which the client which you're going to install on your desktop or your mobile phone as such. And that client is always looking into a particular folder, that is a sync folder, or number of folders, and in which it is always is kind of monitoring the changes to the file and it uploads. That's what the whole idea of the system design of Dropbox or Drive or any file sharing service for today. So now let's talk about the scale of the service which I'm going to, which we are planning to design today. So I actually don't know the Google Drive number of users. It could be enormous, but I'm going to just take the numbers which I got it from the Dropbox. Okay, so far they have about 10 plus million users, unique users, and about 100 million requests are happening per day, and they have a lot of writes and reads happening to their system. So writes in the sense, even it includes the updates and new files uploading, and reads as in, so it's just like downloading or just viewing the file using their services. And here is the system design diagram over here. So you just saw the Dropbox system design diagram, right? So it is full of complex components in it. So before I explain all of these components individually, I want to tell you something exciting, or I want to actually convince you guys or explain you guys what is the core problem in file uploading and downloading services. Because there are a lot of assumptions about designing the Dropbox. Like whenever I talk to people like how do you design Dropbox like services, what they say is all you need to use is some cloud services, and then you just upload the file and download the file whenever you want, and that's simple, right? Because that's not how it works. The problem is very kind of different problem. So I'm going to explain all of that and tell you exactly what problem and how we are going to solve that. So to explain that, so consider this is you and you have a file. Say for example, this file size is about 20 MB. So let's consider that the file size is 20 MB, and this is a big enormous text file where you have a lot of text content inside it. So now for the first time, okay, you don't have any service as such. You have a file, you have a cloud service, say it is Amazon S3 or something. And very important thing is in this session, we are not going to talk about how do we actually build those, cloud file storage or something like that. Let's go ahead and use Amazon S3 or any Azure services, which just keeps the file in the cloud and it scales like anything, and we don't care about it. So we in this session, let's concentrate only on how we build the Dropbox like services, and we don't concentrate on how do we build the cloud storage. We just put the file or blob or anything into the cloud service, and the files will be saved, and whenever we want, we can retrieve it back. Okay. So now it is S3 or something. Okay, fine. Now we have only three components, that is you, the file, and the cloud. So now for the first time you have the file which is of 20 MB. Now you want to share or upload it to the cloud. What you do is you take this file, upload it into the cloud, and you have that file over here of 20 MB. Okay, now all good. Now you get a unique link to this URL or something you share with your friends or something like that. Now, the next time you might want to update this file, two things might happen. One thing is you might have the file locally, or if you don't have the file, you will download it back to the your laptop or something, and you edit it. Once you edit it, you also want to upload it back to the cloud so that you can share it again or save it into the cloud. So now what do I do is upload it again, thinking that I have a local copy, and then I upload it again. Fine. We might do two things on the cloud service. One thing is we might overwrite the already existing file, or we might create one more copy of the file. Now consider we want to support the historical, we also need to know what was the historical updates to the file. So let's keep a copy of the file. So the second file, the version 2 and the version 1, that is also of 20 MB will be uploaded to the cloud. Now, carefully observe, when the first time we updated or uploaded to the cloud services, we use 20 MB bandwidth, and the second time also we use 20 MB bandwidth, right? So total 40 MB bandwidth utilization, and in the cloud storage, we are consuming almost like 40 MB storage. And if I do one more update, I will upload it once again. Now again, I'll consider, I'll use or consume 20 MB bandwidth, and I will create one more copy of the file, that is third version of 20 MB again. Now, do you see some problem over here? I don't know whether you guys see it or not, but let me explain. See the bandwidth consumption. For the 20 MB file, for the 3-time update, even when we update a little bit, just one character correction, or even if it is a big correction, we almost consumed about 60 MB of the bandwidth. And in the cloud also, just to keep a copy of the files or historical review, versions of the file, we consume about 60 MB of the file. And this cloud is costlier, right? And also, you need to pay dollars to every MB you are saving in the cloud service. And also, we are consuming the bandwidth. What if this was about 2 GB file? How much time does it take to upload the 2 GB file and download the 2 GB file? It at least take too much of time to upload and download. And also, if it was a 2 GB file, we would have easily consumed about 6 GB of bandwidth and also 6 GB of cloud storage over here. Now, given this problem, let's see what are the problems listed here. So the first one is upload or concurrency. Now, what happens is, say you try to automate the process of upload and download. Now, consider you wrote a Python service, .py service, which kind of monitors the changes to this file and uploads automatically. Now, what this Python file will do is, what it can do is it looks at the file as a whole, and whenever you click a button to sync, the whole file will be uploaded to the cloud, and that's what it does. Okay, now what it does is it has to take the whole file and upload it into the cloud. So if you closely observe, it is kind of taking the whole file and uploading it. So I can write a script with having multi-threaded or multi-process threaded operation to sync the file so that the operation is faster. Can I do that? Now I can't actually do that because it's a whole file. I can't just write a script which is multi-threaded to just upload one file. It's kind of difficult, very difficult, right? And that's the concurrency problem. You can't actually make use of the concurrency to upload the files to make the upload operation or download operation much faster. And that's one problem, okay? And now let's come to the latency. So if it was about 20 MB, consider like to upload 1 MB of the file, it is taking 1 second. Now if we have to wait about 20 seconds to upload, or even we have to wait 20 seconds to download, we can't do optimization on that because the whole file is uploaded, whole file is downloaded. We can't just do any optimization there. And also related to the bandwidth. So how much bandwidth it is consuming? Every time even if I just edit one character in the file, I'm actually uploading about 20 MB of the file to the cloud, and also I'm saving 20 MB of the cloud storage that is the storage full problem. Just to keep the different history or the version of the file, I have to keep the whole copy of the file just because we edited one character in this 20 MB file. So this is kind of totally a bad idea. This is what we initially think when we want to design file upload or sharing services. So now let's sit back, relax, and design in a different way where all of these kind of problems are solved. So what do we do? So what we can actually do is, instead of rethinking the file as a whole, one, yeah, instead of rethinking the whole file as one entity, let's think differently. What we do is, let's break this file into multiple chunks. Say this 20 MB file, right? 20 MB file. I'm going to break it into, say, 10 different pieces. What I do is, I'm going to break this file into 10 different pieces. Okay. Now I have broken this file into 10 different pieces. Now I call this each of these pieces into chunks. So there is first chunk, second, 3, 5, 6, 7, 8, 9, and 10. There are 10 chunks, and each chunk is obviously 2 MB in size. Fine. Let's revise the whole scenario which we just discussed. So now for the very first time, I have a text file of 20 MB. Now I want to upload. Obviously, for the very first time, if I'm uploading to the cloud storage, I'll have to upload all of these chunks to the cloud. It will take 20 MB of the bandwidth and 20 MB of the storage. So I'm going to write it somewhere here. So the version 1, 20 MB. Obvious, right? It took 20 MB of the file storage. Now all good. Now the fun part is, now I just updated one character in the file in the chunk number 5, or in the position where there's chunk number 5. So now I want to sync the file to the cloud. What do I need to do? Instead of uploading all of the file to the cloud, I just need to sync this 5th chunk only, because that's where the update has happened. Now, if I want to sync this, what is the size of the chunk? I'm going to just sync this chunk that is of 2 MB only. And in here, instead of keeping the whole file, I'm just going to save just 2 MB chunk, and I mark it as second version file. How cool is that? We just consumed 22 MB of the cloud storage. In the bandwidth also, we just consumed 22 MB only. And now the very first problem, right? Concurrency problem. How do we solve that? Consider I wrote a Python script .py. Okay. This service, what it does is, say have about 5 threads in it, and each thread can take a chunk and upload it. So as I already mentioned, if we are taking about 1 second to upload 1 MB, then obviously earlier we used to take about 20 seconds, right? Now, how much time does it take? It will just take, to sync the whole file, we just take 20 seconds divided by 5 times, almost like about 4 seconds only. Earlier we used to take 20 seconds, now we are just taking 4 seconds. And so that's what the optimization. So the latency is very less because we can sync the chunks parallelly to the cloud. Okay, and here, instead of actually saving the whole file, we are kind of actually saving the chunks. The very first file which I have written here, it's not the whole file. It will be like 10 different chunks of the files which is saved in the cloud. And in the second time, we only have one chunk. In the third time, maybe if I edit this particular part and this particular part, now I just need to sync these 2 chunks only. Now in this update, we only got, use 4 MB of 4 MB of bandwidth, and also in the third version, we only keep these chunks 2 MB, 2 MB, okay, of these 2 chunks which was updated. Now think that you have one more mobile devices where you want to keep on syncing this file there. Now, there also, the bandwidth consumption will be almost equivalent to this much. In earlier case, it would have been like 3 times the file will be synced. It will be like about 60 MB of the file, bandwidth utilization to your mobile device. But in this case, it just consumes about 26 MB only. And you can, in mobile device also, you can just use concurrency to download these chunks. So there will be a faster sync in the operation. So this is the radical approach which will help us to design next generation fast service, fast file sharing and upload service. And now you might be thinking, now somehow we divided this file into chunks. Now, who tracks all of these chunks? How do I know what chunk belongs to what file as such? So now I just explained you with one file. If I had about 10, 15 files, there will be like chunks all over the cloud, right? So how do we know that? To solve that problem, what we need to do is we need to have one more file that is called as metadata file. What this file contains is this chunk information. Maybe we take a hash of the chunk and we mention all of the hashes, 10 different hashes, and maybe their locations or something like some reference to this chunk should be there. Some reference to the chunk should be there in this metadata file. And this metadata file also can be synced into the cloud metadata file, and that metadata file can be downloaded whenever we want, or that also saved there. Basically, metadata file gives you the indexes to all the chunks of the file so that we can download all of the chunks. Even when we are downloading, we can actually use concurrency so that we can download the file faster, and we can stitch back all of these chunks to get a complete file using this metadata file. Okay, so this is the very core or important part which you guys need to understand in designing, any of the file uploading or downloading services, and this way we can solve all of this kind of problems. So one such services is like HDFS, right? Even HDFS deals with gigabytes or petabytes of the file, and it actually does the same thing. It actually divides the file into 64 MB chunks, and it distributes the file in different machines so that it can give the backup of the files and duplicate. It can save the duplicate copy of the file easily. So even in this case also, if you want to distribute across different machines and everything, it will be much easier to play with the chunks instead of one whole file. And that thing will actually happen inside the cloud, and that actually will be taken care by Amazon S3. And it will be much easier for Amazon S3 services to handle the small chunk of the file instead of a very big file. So these are the advantages of having a chunk-based operation instead of playing with the whole file. So now let's see the very basics of the system design for any of the file uploading services like Dropbox or Drive. So basically, as I explained, you will have a client. The client can be some application which is installed on your laptop or computer or your mobile phone, or it could be even web app which you can open via browser. So now let's only concentrate, let's think that this client is somewhere installed on your phone or your laptop. So what are the very basic components in the client we should have to provide the seamless upload of the file or the syncing of the file between devices or between clients? So basically we have about 4 different components in the client itself. So now I have only represented one client over here. Maybe we'll have one more client, even more clients. Say, let's consider this is client number 1, client number 2, client number 3. And all of these clients belong to the same user. Let's think that and proceed to our design. So now we have 4 different main components in the client, and this is the folder which has files. And this client is actually actively monitoring the folder and the file changes or updates happening to the files inside the folder. And also here we have a cloud storage service. For the simplicity purpose, let's consider Amazon S3 or any other block store cloud storage services where it just saves the piece or the chunk of the file or any of the file. So now let's consider Amazon S3. And here is the messaging services. This is a queuing or asynchronous messaging services which you can use RabbitMQ or ZeroMQ or Kafka. And then there is a sync service. I'm going to explain that. And there is a database and also cache. Now I've just represented one DB over here. For now, you consider it as DB and also cache, and that's where our metadata will reside. Now, this system on a big picture, how it works, I'm going to explain it now. So now this is a client. We have indexer, chunker, watcher, and internal DB. The very first thing we want to learn is this is the folder. We have configured this client to keep monitoring this particular folder or the files in the folder for any of the changes. So the very first time the folder will be empty. Well, and we have configured to monitor this folder, right? So this watcher will be watching this particular folder. As soon as we put some files into this particular folder, this watcher will get notified that there are a couple of files which has been added to the folder. What this guy does is it notifies the chunker and indexer that there is some changes has happened to the folder, and it also passes the path to the files to the chunker and indexer. What chunker does is, as the name indicates, it makes this file into multiple chunks and then it uploads into Cloud S3. Before it doing so, it actually computes the hash of each chunks, and that will be kind of unique identifier for the file and the chunk, and then that will be uploaded, and that hash along with the URL which we got back from the cloud services after uploading the chunk will be given back to the indexer. So, and then what indexer does is it receives the URL from the chunker and also the hash of the chunk, and it will update that particular information in the internal DB against the file for which those hash belongs to. So now everything is good, right? So we have already uploaded the chunks of the file to the Cloud S3. That means that the complete file is already uploaded there. And we also, the indexer has saved the hashes and the URL to those chunks in the internal DB. Now everything is good. Now what we need to do is this indexer will notify the messaging services. Sir, here is the file which was we saw it newly on the folder, and we have made it to these many chunks and we have uploaded it there, and all this information will be passed to the messaging service. It is just a queue. What this indexer will do is that message will be sent to the messaging pipe or queue, and that message will go here, okay, and then that message will be picked up by the sync service or synchronization services. What do we need to do so? Because initially I mentioned that there can be multiple clients which belong to the same file. As soon as we add a file into the folder, the same thing should be replicated on the other devices, right? So that's the main reason why indexer should notify the messaging services or synchronization services that there is some modification to the file has happened, or there is an addition or deletion to the deletion of the file has happened. So that's when the synchronization service, what it does is it also updates the metadata into the metadata database. Usually it is MySQL because we need it to be consistent. The data of metadata, the data of the chunks or the hashes should be saved in a consistent manner. So for now, let's consider we're using MySQL DB, and we update all of this information into the database. And also what sync service does is it sends back some of the messages back to the one more queue which is there in the messaging services, and those messages will be broadcasted to the other clients. So what happens is this guy send back this information of updates to the file back to all of the clients which belong to that particular user. So now these guys learned that there is some file addition happened to this folder. Now what we need to do is they also obviously have the same kind of components here, and the indexer will now fetch back those chunks from the cloud and rebuilds the file or syncs back the file into their devices. So basically, as soon as this messaging services sends the messages to these clients, what happens is the indexer there will get back all of these chunks of the file, say for example these two files chunks, and then inside the folder they will recreate the files. So they will have two different files, exactly similar copy of these folder and files will be replicated in other devices. Say I said this is device 1, device 2, and device 2, right? Now the same copy of the files is replicated in all of the three devices. So that's how it works. Now I'm going to explain each of these components a little in depth, okay? So now let's learn about the messaging service. You might be thinking, why do we need a queue over here? Whenever we saw that some file updates are happening, why can't we just talk to the sync services synchronously? Why do we need an asynchronous messaging service over here? I'll answer that question. So this is the little bit more in-depth view of the messaging services. So you can think of the whole thing as a messaging services. It is basically n number of queues will be there inside it. So consider for the simplicity purpose, n number of clients. There will be n number of queues will be there, plus little more queues will be there for different purpose. I'm going to explain that. So there are two types of queues in it. The first one is request queue, and the second one is response queues. Why do we need request and response queue? I'll explain that. So consider there are three clients as I mentioned earlier, the client number 1, 2, and 3. We have a file. The client number 1, or the client which is looking at the file, saw that there is some changes happened to this file, or that file was newly added. So this guy will upload into the cloud service, and now it knows all the information about the chunks and the metadata information, right? What this guy does is he posts all the metadata information to the request queue. Why do we need a queue is, so this guy sends all of the metadata information to the request queue of the messaging services. Why do we need to do the asynchronous way is, because these devices might be connected to the internet or might not. We can't just always rely in a synchronous manner to send the updates about the files or sync the files, right? So we might be connected or we might not be connected. So we need a mechanism where these updates are kind of buffered and sent back to the server, and get the information, the metadata information about the files in asynchronous way. That's the only reason why we need messaging services or queues. So what this guy does is he posts the metadata information to request queue, and that message will be staying here. And then this queue will be connected to the sync services, and then that message will be read by the sync service. And as I mentioned earlier, sync service will update the information into metadata store, that is metadata DB and cache. That all happen, and also the sync service will broadcast back to all the other clients for the same user, which is registered in RDB. What this guy does is, whatever information which it received from the request queue, it rebroadcasts all of those messages to the response queues. What happens is all the same metadata information will be sent to the response queue 1, response queue 2, response queue 3. That information will be there inside this queue, okay? So now, again, the queue helps you to buffer these updates. If these two clients or these three clients are disconnected, now that message will stay in the queue, will never get lost. If it was a synchronous service, this guy should have called directly to this client by some way, by HTTP. That doesn't work because these guys might be connected to the internet or to the server or not. So we put all of the metadata information to the response queue, and whenever we learn that these clients are connected to the servers, this metadata information will be delivered. As soon as these clients receives that metadata information, they know what to do with that. So they know the URL from where they should fetch those chunks and then update their respective files. If they don't have the files, they will download the file and keep it synced. Otherwise, they will just download the chunk which was updated from the client one and they update the file. And now let's learn what are the information which is stored in metadata. And also let's learn about metadata database and its own internal architecture to make it work seamless. At Dropbox, they call it as Edge Store. This is just for your information, okay? So now, what are the information which we want to store in metadata database and why do we need it? So the first thing is metadata database or metadata information will actually contain the information about the chunks and the hash, right? And also it contains the information of the file and its version, because every chunk is kind of mapped to the different version of the file. So that information is also captured. And also along with that, it also contains the information about the user and what workspace they were working on using any particular client. And now what kind of database we should be using for metadata store. So we can actually use RDBMS or NoSQL. Irrespective of that, what we need importantly is the consistency, because multiple clients will be working on the same file, right? So we definitely need a consistent data to be stored in our metadata. Even though we're not actually saving the whole file content into the DB, the metadata information will itself represent the whole chunk or the file. So we need this metadata to be, consistent across different clients. So we need a DB which acts more consistent manner. So the very good thing about RDBMS is consistency comes inbuilt in the RDBMS. But whereas you can go for NoSQL, the only problem is it is eventual consistency that might screw up your file or chunks. You might be wondering, okay, what happened to the file? Where is my version? I edited this and this is gone and this part is there and this part is gone. So all of these problems will come back if you use NoSQL. Or if you still want to use NoSQL, we have to have a layer on top of the NoSQL, which actually protects you or which actually gives you the consistent writes to the NoSQL, because it is generally proven also that NoSQL scales well with more data as we store. But nevertheless, Dropbox guys have managed to use MySQL and scale it to the existing user base, about 10 to 15 million users, and tons of millions of files of metadata information using MySQL itself. And I'm going to explain like how actually they did it. As I mentioned, that is called as Edge Store, and that's architecture is over here. And before learning about what is this, we have to also learn the structure of information which we want to store. That is the actual metadata. And this is how it looks. So this actually is a kind of JSON which has these information, which has chunk ID, which has chunk order, and all the information about the object. Why do you need a chunk order? As I already mentioned, that if we break the file into multiple pieces, we should also know the order at which the chunks should be, stitched back to get the original file. And also in the object information, we have the version number, whether it itself is the folder information or it's a file, and that information is captured in each folder, and also the file name, obviously, and the extension, size, and path, etc., etc. And also a little bit information about the user is also captured over here, along with the device information. So now let's learn the internal architecture of the metadata, service itself. That is not actually simple. In this diagram, you might think it is just a DB, or you might have one more layer of caching, or you have a separate caching component over here, but it's not actually easy. Let's go ahead and design using MySQL itself. When we think of RDBMS, it is kind of difficult to scale, because to scale, we had to either do sharding or what we can do, master slave and all that, right? And those are a little difficult. What Dropbox guys have done it is they have used sharding technique to distribute the data across multiple, MySQL instances. They don't just have three MySQL database, they have like thousands of database over here. Not just the metadata information, they have all the other information also stored in using the Edge Store itself. So the very basic problem when you're using multiple database which is shared is so when we decide to use MySQL database to store the metadata information, what are the problems we might face? Consider this system is not there, we just have database which the metadata is shared across multiple database. So for developer, it is a significant burden where they have to keep on validating the schema and everything, right? It's kind of difficult task. And the next thing is whenever the database is filled and almost filled, we should be keep on adding more database to accompany more information or more data, metadata information, right? We might need to rebalance all of the data and reshard. This is kind of real pain. And the real big challenge is making these machines or managing these machines to be always available like 24/7, right? These are like difficult problems. To solve all of this problem, what Dropbox guys actually does is they kind of built a wrapper around this sharded database, and they built APIs for the clients which actually interacts with the Edge Store or metadata store. So the clients, they have more of like Go or Python. Say they directly, instead of the clients directly interacting with the database, they started to interact with the Edge wrapper, which kind of provided a ORM, that is object relational mapper, which is kind of abstracted away, right? So the clients just call this, uses this ORM and just interact with the database. How easy it is, right? And they have an engine which kind of transforms all these ORMs and then interact with the MySQL. Everything happens internally. And also, obviously, not every time when we want to fetch the file, we have to get this information about the chunks and everything, right? It's it's not a good idea to every time to fetch from the database. So we have to obviously have a cache in between. So if it didn't have the system, we would have had cache separated. First thing is we check in the cache. If it is not there, go back to the database and fetch it, right? So this system internally provided all of the services out of the box. So the developer need not to actually, check in the cache and then query in the DB, but instead this edge wrapper itself kind of figured out that particular information is already available in the cache or not. If it is not there, then go to the engine, unwrap the ORM, and get that all the information about the file which they are querying from the database. It is that convenient to have a wrapper, around the MySQL. And also the advantage is we never need to know about the underlying database. And also the Edge store by default provided the transaction isolation between different queries the clients are actually making to the database. So that way we don't need to worry about having a lock or having a transaction when we actually writing something into the meta store or Edge store or the metadata database, right? So it is kind of out of the box provided by the Edge store in a different layer like Edge wrapper and engine. So now let's talk about how to serve the data in scale. As we know, we have about more than 10 million users, thinking that 10 million users, and we'll have more than 100 millions of the files, best case. So how do we serve all of this data at scale, faster, lightning faster? How do we do that? So considering that we are using Amazon S3, Amazon S3 has more than about 9+ region presence, right? So think that they are automatically distributed using CDN, Amazon's own CDN. Now we also need to make strategy based on the user's home location. If the user is from Singapore, we have to place that file somewhere near to that location, that is Singapore. Amazon, I think, has about in the Singapore itself, right? So we can actually upload all of these chunk files into the Singapore data source, data center itself, so that whenever that user wants to sync that information, he can download it as fast as possible. And that is kind of solved because the Amazon itself is providing services. But when we are talking about metadata, because without metadata, no client can download anything. So metadata is actually the key information to download all of the file. So since we are the one who are storing all of this metadata information using XStore in MySQL, we have to actually place this information also much closer to the user. What we need to do is we have to either use some CDN services like Akamai, Fastly, or any of the CDN services, or we have to build our own CDN. How do we do that? First, we need to find out where our users are from. If there are like more users from Asia, we have to obviously need to place a data center or some servers near to Asia for Asian users. So how do we do that? We can actually use some kind of shallow learning methods like k-means clustering or some kind of clustering algorithms to find out the group of users or the clusters of the users from different region, and we have to place the server somewhere near to that region. So actually Dropbox kind of did the same. They actually clustered the users and they have placed the CDN or edge servers near to the user. What this information, so what the servers contains is the metadata information, because without metadata, we can't download any of the file from Amazon S3. Look at this first picture in which this explains, say, consider the metadata information and the data both are kind of stored in US region. If a user from Europe wants to download it, it is kind of taking about 700 milliseconds. But wherein if you decide to place the metadata server somewhere near Europe itself, a user can actually download the file or at least get the metadata information and contact the actual Amazon S3 cloud within 330 milliseconds. That's how actually we have improved the latency by the factor of 2. And that's the advantage of having CDN. So far we learned how exactly the file sharing and upload service works and its system design. Now, before I end the session, I just want to give some ideas on how we can actually implement the search engine, the full text search engine for our service. So we want to provide customized search feature from our client application, which our users have installed on our laptop or mobile phone. How do we do, or what are the different ways we can achieve that? So I just want to throw some ideas on that. You guys read about it because there are a hell lot of articles about how do we implement search engine using machine learning and NLP, that is natural language processing. First thing is we have a lot of files with us. Before we actually upload these files into the cloud, we can do processing there in the client, but that is very tedious process. We can't actually apply all of the different machine learning models or train them. So what instead we can do is we can actually have a background running process or a scheduled job in our data warehouse, or in some data center where we actually look into all of the files which the users are uploading, and then in a weekly manner or bi-weekly manner we can actually look into all of these files and extract the text information from there. If it is all if all of the files our users are using are kind of text files, it is much easier to extract all of the text information to provide the search feature. But we know that people might be uploading, text files, PDF images, or sometimes videos also. If you really want to provide some kind of search, if you look at the Dropbox or Evernote, they actually provide the image text search also. How do we actually do about it? How do we actually do some kind of processing about it? So if it was a text file, we can easily extract all of the text, and then we can do natural language processing and apply all of these different techniques like tokenization, removing the stop words like articles the, to, and, or something like that, and find all the synonyms using WordNet, which is a lexical dictionary which is available in the internet for free, and stemming and lemmatization techniques to get the actual words and to understand the actual context or context of the sentence and give a better search results. So if the file was PDF, image as or videos, how do we do about it? So there are different strategies to that also. First thing is we can either take the PDF files, take the we can pass the PDF file, but if we can't pass the PDF file, what we can do is take the image screenshot and then convert it into image. Now we have PDF and image both as an image form. And now what we can do is we have to extract the textual information present inside those images. If it is PDF, definitely we are expected to have a lot of textual information there. But if it is image, we might have or we might not have. First thing is we should have a high level of some kind of algorithms like machine learning algorithms which can detect whether there is a text information there in the image or not. We can actually use convolution neural network or CNNs to do that, which are very good in image processing. And we can actually leverage optical character recognizers or OCRs to actually do that task to figure out the letters in it. What people actually use is if the image is kind of tilted, the texts are not always properly horizontally oriented, right? The text could be tilted in any direction. People these days are using deep neural networks to actually rotate the image so that we can actually extract the text part and then provide it to the OCR or convolution neural network to figure out what kind of textual information it is there, and then get that textual information and then tag that particular position on the image, and etc. So when the user searches, actually you can actually show image highlighted for the text also. That's kind of way cooler feature you can provide in your document too. And basically we have to keep on looking at the signals from the user interaction, and whenever the file updates happens, we need to keep on rerunning all of these processes which I just discussed to build the search indexes up to date. I think I have covered most of the information which is needed to design the file sharing and file upload services. I think it's time to end this session. Uh, as usual, if you guys have any suggestion, please do send it to me. If you want me to make any of the videos on any of the system design, please drop me a comment. I'll pick one of the system design for the next week. Thank you as usual. Please don't forget to subscribe to the channel. It actually encourages me to keep on producing more of the system design videos. And also please tell your friends about the channel and then make them subscribe too. Thanks a lot.